The commonest argument against mechanical doping is a weight argument, and you have heard it 100 times. No professional would carry 2 kilograms of motor and battery up a mountain for a modest gain in power. The weight would cost more than the motor gives back. It sounds decisive, so let us actually do the arithmetic, properly, with the assumptions stated out loud, and find out whether it is true. First, the ground rules, because a calculation is only as honest as the numbers you feed it. Everything that follows is a calculation, not a measurement. Nobody has ever put a rider with a concealed motor on a mountain and timed them. What we can do is take real published figures, apply the physics that governs climbing a hill, and see what falls out. Here are the inputs. The climb is a real one, the Alpe d'Huez, 13.8 kilometers long, averaging 8.1%, gaining roughly 1,100 meters of altitude. The total mass going up it, rider plus bicycle plus clothing and bottles, is 76 kilograms. And for the rider's own sustained power, we are going to assume 300 watts. That last number is an assumption. It is chosen for illustration, not taken from any athlete. It is a good, strong amateur's sustained climbing power, and it makes the arithmetic legible. If you prefer a different number, the proportions do not change, and that turns out to be the whole point. Now the physics. Climbing a hill is almost entirely a fight against gravity. The work needed to lift 76 kilograms through 1,100 vertical meters is mass times gravitational acceleration times height. That comes out at about 820 kilojoules of pure lifting. Add rolling resistance and air drag, which on a gradient this steep are secondary but not nothing, and the real total lands somewhere around 930 to 965 kilojoules. At 300 watts, that takes roughly 3,100 seconds. Call it 52 minutes. Now add a concealed seat tube motor. The commercially available unit, the one that has actually existed and been sold, is quoted at a complete system weight of 1.8 kilograms, and testers who have ridden one describe a boost of around 100 watts. Note that word describe. That figure is a description from published testing, not a laboratory measurement of crank power, and it should not be dressed up as one. So the rider is now producing 400 watts at the wheel instead of 300. Run the same sum. Roughly 2,300 to 2,400 seconds. Call it 40 minutes. 52 minutes becomes 40. The motor saves about 12 minutes on that climb. 12 minutes. On a mountain where the entire history of the race is separated by 2 or 3. It is worth pausing to sanity check that, because a result that large should make you suspicious. 300 watts on a 76 kilogram system is about 4.4 watts per kilogram, and 52 minutes for this climb is exactly what a strong amateur does. 400 watts is about 5.9 watts per kilogram, and 40 minutes sits just outside the fastest times ever recorded on the climb by anybody. The numbers behave sensibly at both ends, which is what you want from a model before you trust what it says in the middle. And notice what that second figure means. Adding a modest concealed motor to a good amateur does not produce a good professional. It produces a time in the neighborhood of the greatest climbing performances in the history of the sport. And before anybody objects that this depends on the climb chosen or the rider assumed, it does not, and here is why. On a sustained climb, gravity dominates everything else, which means the time taken is very nearly inversely proportional to the power applied. Going from 300 watts to 400 is multiplying your power by 1 1/3, which divides your time by 1 1/3. That is a reduction of about a quarter, about 25% off the climb. Whatever the climb, whoever the rider. Now the other side of the ledger, which is the actual question we came here to answer. What does the weight cost? 1.8 kilograms added to 76 kilograms is an increase of about 2.4% in the mass being lifted. Since the work is proportional to mass, that is about 2.4% more work, and therefore about 2.4% more time. 2.4% of 52 minutes is roughly 1 minute and 15 seconds. So there it is. The weight costs about 1 1/4 minutes. The motor buys about 12. The trade is roughly 10 to 1 in favor of carrying it. That is the answer to the weight objection. And notice that it required no clever argument about rulebooks at all. Even paying the full weight penalty, every gram of it, the motor wins by an enormous margin. The objection was never a good one. Which brings us to the argument that usually gets made at this point, and to the reason this video is going to be harder on it than most. The clever version says the weight is not even paid. Professional bicycles have a legal minimum weight of 6.8 kilograms, set by Article 1.3.019 of the Technical Rulebook, a figure devised in 1996 and confirmed around the turn of the century. Modern frames can be built lighter than that, so teams add dead ballast to bring them up to the limit. Metal weights hidden in the seat tube near the bottom bracket, heavier handlebars, metal-railed saddles, stainless steel pedal axles instead of titanium. One well-known American frame builder has described riders dropping a sock full of coins or fishing weights into a track frame to make the limit. The argument then goes, you are not adding a motor to a bicycle, you are swapping useless ballast for a motor, so the weight is free. That argument is much weaker than it looks, and it is worth being straight about why. When bicycles were weighed at the 2026 Tour de France, the sample averaged just over 7 kilograms. Not one of them was under the legal limit. One sat exactly on it, and the rest were above, some well above. Disc brakes and electronic group sets have added enough weight that routinely building under the limit is no longer standard practice. And even on a genuinely featherweight climbing build, the ballast involved is in the region of 800 grams to a kilogram. That does not absorb 1.8 kilograms of motor and battery. Roughly half of it is still paid, on the most favorable bike you could pick, and all of it on a typical modern one. So the honest version is narrower. The ballast argument had real force in the rim brake era, which is precisely the period the loudest allegations come from. It has much less force today, and it was never necessary to the case anyway, because the arithmetic already works without it. One more thing, and it points the other way. Put the same mass in a wheel rather than in the frame, and the trade gets worse, not better. Mass at the rim has to be spun up as well as carried, so it penalizes every acceleration, every change of pace, every response to an attack. That is engineering reasoning rather than a measured result, but it is sound, and it explains something about the reported wheelbase systems that is otherwise puzzling. They carry a real rotating weight penalty for a fraction of the power. They only make sense if what you are buying is not speed. If you want the documented record on this subject rather than the rumor, subscribe to the Peloton Files. So the weight objection, the one thing everybody reaches for when this subject comes up, does not survive contact with a calculator. Not because of a loophole in the rulebook, but because 100 watts is simply worth far more on a mountain than 2 kilograms costs. Which leaves the sport in an awkward position. The reason nobody has been caught at professional road level cannot be that it would not be worth doing. On the numbers, it would be worth doing enormously. Whatever the explanation is, it has to be something else.